Hello everyone, welcome to today's live broadcast, Challenges in Extracting Perfluorinated Compounds in Drinking and Wastewaters. I'm Ali Matheson, the Editor-in-Chief of LCGC Europe and the column, and I will be your moderator for today's event. We are very pleased to bring you this web seminar presented by LCGC and sponsored by Biotage. Together with Horizon Technology, Biotage will be able to offer its global customers an even more comprehensive portfolio of products. Horizon Technology is a world leader in automated sample preparation. With over 20 years of experience consulting with lab managers and regulatory agencies, the company has developed an in-depth understanding of processes, chemistry compliance requirements, and operational challenges. This knowledge has driven the company's progress in automated technology and the expansion of its product line to meet the needs of laboratories worldwide. For more information, please visit www.horizontechnic.com. We have a few important announcements before we begin. This webcast is designed to be interactive and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of your screen. You can enlarge the slide window by clicking on the small green icon in the upper right-hand corner of the slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the event. If you have any technical problems viewing or hearing this presentation, please click on the question mark help widget in the dock at the bottom of your presentation window. Before I introduce today's speakers, I'd like to ask our audience to participate in two very brief polling questions. Please click and enter your answers directly on the screen. Here is the first question. Are you currently extracting PFC compounds from method 537 or from method 537 modified on the DOD list? Method 537 or method 537 modified? I'll just repeat that. Are you currently extracting PFC compounds from method 57 or from method 537 modified in the DOD list? Method 537 or method 537 modified? Thank you very much for participating in our first poll. I'd now like to ask our audience to participate in our second polling question. Please click again and enter your answers directly on the screen. Here is the next question. Are you currently using manual or automated extraction for processing samples for PFCs? That's A, manual, or B, automated. I'll just repeat that. Are you currently using manual or automated extraction for processing samples for PFCs? That's A, manual, or B, automated. And again, thanks very much for participating in those brief polls. I would now like to introduce today's speakers. We are pleased to be joined today by Maura Rourey and Michael Ebbetson. Maura is the Regional Marketing Manager for Horizon Technology, where she develops and executes marketing strategy to support workflow solutions for applications in applied science market segments, including food and beverage, environmental, petrochemical, and industrial. Maura received her ACS Certified Bachelor of Science in Chemistry from Union College and her PhD in Analytical Chemistry from the University of Massachusetts in Amherst. Michael is the International Service Manager at Horizon Technology, where he coordinates with applications, field sales and service, a network of over 40 international distributors to provide technical support and customer satisfaction to current and prospective customers. Michael received his Bachelor of Science in Biology from Westfield State College with a minor in Chemistry. And thank you both very much for joining today, and if you could start the presentation, that would be great.
Hi, my name is Maura Rourey, and thank you for joining us today. I will be presenting challenges in extracting perfluorinated compounds in drinking and wastewaters. You hear the term perfluorinated compounds, or PFCs, in the news a lot these days, but there's often quite a bit of confusion when it comes to the terminology that's used. You hear the term PFCs and then you see a news headline that references PFOAs and you think, wait, are those the same things? And then a reference will be made to PFAAs and you might think, but wait, I thought they were called PFOAs. The term PFCs refers to an entire class of fluorinated compounds, which means they have at least one carbon-fluorine bond. The physical and chemical properties and therefore the final use of each compound varies and is dependent on the specific functional group that's present. For example, PFOS is a perfluorooctane sulfonic acid, and its chemical properties make it good for use in firefighting foams and in anti-reflective coatings. PFOA is a perfluorooctanoic acid and is used for manufacturing PTFE and is a major component in water and oil repellent products. The examples listed here are just a few of the many that appear in the research and published literature today. Compounds such as perfluoroethers, perfluoroamines, perfluoroketones, perfluoronitriles, and perfluoroalcohols are used in many applications and in many end products. Adding to some of the confusion around perfluorinated compounds is the use of the word emerging when discussing these compounds. Headlines in the news present these as emerging contaminants and combine that term with words like crisis. And you start to ask yourself, how did we not know about these perfluorinated things before? Are we really just starting to discover that they exist? The answer to that is no. We're not just discovering these compounds. These are man-made compounds that have been manufactured for decades, some of them for over half a century. The strengths of the carbon-fluorine bond in these chemicals gave them chemical properties that were applicable in many industrial processes, so these compounds are not at all new. The use of the word emerging indicates that the information about these compounds is emerging. As we monitor, track, and quantify these compounds, information is emerging about just how persistent these compounds are and how that persistence has contributed to their prevalence in drinking water sources around the nation. The persistence and the prevalence of these compounds has given us the opportunity to track its ability to accumulate in the environment and to bioaccumulate in humans and in other organisms. As I've mentioned several times, perfluorinated compounds are highly persistent. Unfortunately, the strong carbon-fluorine bond that gives these compounds the physical and chemical properties that we're looking for in things like fabric protectors, fire suppressants, or nonstick coatings for cookware are the same properties that make them highly resistant to degradation, even when metabolized or exposed to harsh temperature or pH environments. The persistence allows these compounds to hang around and to accumulate for years in our water, food, soil, air, and in fish and animal tissues. The EPA has found that the largest source of PFC exposure is via consumption of contaminated drinking water. When PFCs were turning up in our water sources, the EPA added 6 of them to the 3rd unregulated contaminant monitoring rule list to better understand their prevalence and our exposure risk. As many of you are aware, the EPA uses the UCMR program to collect data for contaminants that they suspect might be present in our drinking water, but don't have maximum allowable levels set under the Safe Drinking Water Act. Out of the 6 PFCs that were added to the UCMR 3 list, PFOA and PFOS gained the most attention. The significant prevalence of PFOS and its potential to harm the developmental, immune, metabolic, and endocrine health of its consumers has made it so that it got added to the official Stockholm Convention list of persistent organic pollutants, otherwise known as the POPs list. PFOA isn't far behind in its prevalence and is now being considered for addition to that same POPs list. PFOA was made famous by DuPont when they manufactured this compound for use in manufacturing fluoropolymers. And PFOS was manufactured by 3M and is known for its water repellent properties and is the main component in a commercial substance we're all very familiar with, which is Scotchgard. Both PFOA and PFOS have been added to a health advisory for drinking water that was issued by the EPA. Under this advisory, water utilities should notify customers if more than 0.07 micrograms per liter or 70 ppt of PFOS or PFOA is detected in the water supply. This health advisory also requires notification if a total concentration for the 2 compounds is higher than 0.07 micrograms per liter. In order to properly measure and monitor PFCs on the UCMR3 list, the EPA developed a method for extracting and quantifying perfluorinated compounds in drinking water. Known as Method 537, this is the method for measuring PFCs in water. It's specific to drinking water and contains an analyte list with 14 PFC compounds. The method dictates that solid phase extraction must be used for preparing samples for subsequent analysis by LC-MS. Although Method 537 was carefully developed and the accuracy and the precision of the method was vetted via multi-lab validation, and the analysis of thousands of drinking water samples was collected through the UCMR program, there are still some challenges that laboratories face. First of all, this method is prescriptive for 14 PFCs in drinking water. It is not a reference method to give you a protocol to follow for any PFC that you want to extract and quantify. So what if you're trying to quantify a perfluorinated compound that isn't in Method 537? The second challenge is in relation to the sample matrix. Method 537 is specific to drinking water. So what if you're trying to measure perfluorinated compounds in a different sample matrix, like non-potable groundwater or soil or sediment or wastewater? As the list of worrisome PFCs has grown and the need to analyze a wider range of sample matrices has expanded, more and more laboratories have sought answers to the challenges and the limitations of Method 537. The current response is what's being referred to as modified Method 537. As the name implies, modifications to Method 537 are being explored to support the analysis of a wider range of perfluorinated compounds in a wider range of sample matrices. This requires modifications to the method, predominantly to the performance and the quality control check requirements. Since there's no single defined set of method criteria, each laboratory must establish their own set of modifications and QC requirements based on which PFC compounds they're measuring and in which sample matrices. Before moving on, I just want to clarify that this is not a new method. Even though it's referred to as Modified Method 537 or 537 Method Modified, these are just modifications to an existing method. There is no published method called Method 537 Modified. I also want to clarify that the modifications being made are not EPA validated. Each laboratory is tasked with establishing their own set of modified QC requirements based on their specific PFC application. Therefore, performance requirements will likely vary between laboratories and may vary significantly based on their specific application needs. Before you see the overview of the modified method and think PFC analysis has become like the wild, wild west, there's a logic and benefit to the changes that are being implemented. Method 537 outlines a protocol for the quantification of 14 PFC compounds in a drinking water matrix. So it actually becomes a logical place to start when you're developing performance criteria for an expanded set of compounds and sample matrices. The method also provides guidance for minimizing background and sample-to-sample carryover, as well as system contamination, which provides the laboratory with a set of useful information for troubleshooting potential data performance issues. Method 537 also outlines the use of LC-MS, which is used for quantification and should provide the sensitivity required for analyzing any additional PFCs. The challenges here are related to the fact that there's no actual official modified method. So how do you confirm that you're accurately extracting and measuring the perfluorinated compounds that aren't in Method 537? And how do you determine what your QC performance should be to determine whether your data passes or fails? The Department of Defense is managing a PFAS laboratory accreditation program to try to help guide this modified method development. The DoD Environmental Data Quality Work Group has been working with the Department of Energy to produce a quality systems manual for environmental laboratories. The QSM provides baseline requirements for the establishment and management of quality systems for laboratories performing analytical testing services for the DoD and DOE. The 14 perfluorinated compounds that you see here are the PFCs listed in EPA Method 537. The compounds that are circled in orange are the 6 perfluorinated compounds that were added to the UCMR3 list. The modified method includes an additional 10 PFC compounds for a total of 24 perfluorinated compounds, and those are listed here. One of the biggest challenges when tackling this application is in minimizing interferences and opportunities for contamination during sample prep and analysis. As PFCs are highly stable and non-reactive, they've become commonly used materials for equipment parts, tubing, and a handful of other laboratory supplies. Additional contamination sources could include the sample collection and storage containers, the laboratory solvents, the standards that are being used for internal and surrogate standards. Even the reagent water could be a contributor. Therefore, a critical step in the method validation process is to accurately prepare and measure blank and fortified blank solutions to demonstrate accuracy without measurable interferences or carryover effects. As with any EPA-validated and published method, there are a series of performance checks that must be completed to validate your laboratory's performance when you generate and report data against a specific method. While the specific requirements may vary from method to method, the overall approach is typically the same. It's important to establish your minimum reporting limits, and those are usually based on some sort of calculated method detection limit. And then, of course, you need to do an initial demonstration of accuracy and precision, followed by a series of quality control standards, fortified blanks, fortified matrix samples, duplicates, and on we go. These performance checks aren't trivial to complete, but with Method 537, the biggest challenge ends up being in the demonstration of low background. As I mentioned a few minutes ago, one of the biggest validation challenges for Method 537 is demonstrating that your method and your instrument does not contribute a significant background concentration. You also have to demonstrate that your method and your instrument don't contribute to carryover effects from sample to sample. So to complete this validation, your solutions all have to pass through the rinse lines, the solvent lines, the valves, the system tubing, all of the solid phase extraction material, and all of the other instrument components. And the results should indicate that there are no measurable PFC concentrations, and your surrogate standards should all be recovered between 70 and 130% of their known concentrations. This presentation will demonstrate the use of an automated cartridge-based solid phase extraction system, which meets the requirements for low system background and provides accurate and reliable results for PFC compounds in Method 537, as well as some of those listed in the method modifications. At this point, I'd like to thank you for your attention, and I'm going to turn the presentation over to Michael.
Hello. Thank you, Maura. Method interferences. The challenges for validation within this method start right from the bench level, with contaminants within ordinary lab supplies like solvents, reagents, including reagent water, sample bottles, caps, and even SPE cartridges. That's due to the fact that the analytes in this method can be found in many common laboratory supplies and equipment, such as PTFE products, the methanol itself, SPE sample and solvent transfer lines. With that in mind, many of those items with PTFE must be routinely demonstrated to be free of interferences, especially 1/3 less than the method, the MRL, for each method analyte. Taking the proper precautions can lead to implementing this method in your lab faster and reducing downtime. Extraction platforms. There's a variety of extraction platforms in the market. There are 3 main platforms that can be used for extracting for method 537. 1, extraction manifold is a manual vacuum manifold for cartridge extractions, has a short flow path, and requires the user's attention at all times. Another is a large volume vacuum extraction manifold. It's a manual vacuum manifold for cartridge extractions with PTFE tubing. Most platforms of this type have standard PFE tubing. This manifold is used for unattended sample loading, which is convenient. The next is the automatic extraction system. Designed for use with 6mm cartridges, with an automated system, the extraction and/or elution steps may not be changed or omitted to accommodate the use of an automated system. Fully automated and does not require attention once a sample is loaded. extraction platform challenges. With any extractor platform, you do have to take precautions to ensure the PTFE commonly used in these systems does not contribute to unacceptable analyte concentrations in the laboratory reagent blank, or LRB. To help lower potential contamination, the extraction platform should be washed, rinsed with methanol, and dried before use. Those actions are needed because perfluorinated compounds are found in many extraction platforms and supplies, such as we alluded before, the PTFE tubing, valves, pump head seals, vial caps, septas, sample collection lines, tubes, and again, the solvent itself used with the unit. Here, we're looking at a vacuum extraction manifold. The standard vacuum manifold. There's two here, one for high throughput and the other for low throughput. With this platform, there's little involved that could self-contaminate, as there's a very small flow path through the manifold into a collection tube. Most of the concern would be with reagents, consumables, and cleanliness of the supplies itself. The large volume vacuum extraction manifold. This manifold is the same as the previous model except for a few components. The SPE sample lines, plugs the bottom, will come in contact with the sample. The sample line, tubes, and sample line filter, possibly PTFE components, all these components come in contact with the sample and will be a factor for contamination when the sample goes through and will need to be demonstrated. The PTFE lines are inside the sample bottle and will be in contact with the sample. Automated extraction system. The image to the left, this automated extractor system has many components, such as valves, pump head seals, tubing, glass plunger, and there are PTFE components. This particular automated extractor is fitted with fluorinated ethylene propylene lines throughout to help limit the analyte contamination found within PTFE systems. If we take a look, there's a valve, PTFE. We have the valve here for our solvents and our samples. We have the sample lines themselves going in that would have to be demonstrated for PTFE-free. And the plunger, which also has a glass outer containment unit, which glass, again, is an item would have to be demonstrated for the LRB because the compounds could be absorbing onto the glass. The image to the right has a FEP line attached into a stainless steel sip tube. These tubes are an excellent choice for having a tube in the sample because you do not want PTFE soaking in a sample or sample bottles. Sample delivery system. The polypropylene sample delivery lines are recommended but not mandatory with any of the platforms. You can use PTFE transfer lines, but an LRB must be run on each transfer line for an initial demonstration of capability to prove there's no leaching of compounds. If there was, it would result in false positives. For automated platforms, the removal of PTFE lines may not be feasible. Therefore, LRBs need to be rotated among those ports and must meet the QC requirements. So you cannot run an LRB only in position 1 on a system. It must be rotated with every single sample position. Solvent transfer lines. Some precautions to take when setting up a system. Compounds can build up in the PTFE solvent transfer lines when left submerged or purged from methanol. So you must not leave the lines in solvent bottles if they are made up with PTFE. That will contaminate the entire source, thus leading to sample-to-sample contamination and within your system. So care must be taken, and you must clean and clear out the lines when finished running, especially at the end of the day. You got to ensure that you do this manually by purging out with nitrogen, or the automated system itself has functions in which you can purge those lines to ensure no carryover cross-contamination. If desired, the solvent transfer lines, either manually or automated, can be replaced with PEEK tubing. PTFE solvent frits also should be replaced with stainless steel frits if possible. If it's not possible to remove all background contamination, but these measures do help to minimize the background levels. You will be able to achieve lower MRLs and achieve the method requirements for low background by taking these precautions. So here we have PTFE contamination being demonstrated. So we have results with PTFE solvent transfer lines. We have a system here with a blank LFB 1 through 4. And position 1 on the system has run a number of times. As we can see here, it has a non-detect for PFOS. Line 5, which is the LFB4, has been run a number of times as well and has achieved results that are acceptable at 109%. Lines 2 through 4, though, these lines haven't been run as much and have received little if no methanol purging. These results are out high and false due to PTFE contamination. Sample delivery and solvent rinsing. Brought it up before, it's a little further away, but wanted to show that this is a close-up picture of the stainless steel sip tube in a sample container. This can also be placed in a solvent bottle to ensure no leaching of PTFEs will contaminate your source in the solvent, or if left over time, potentially the sample. The rinsing feature on top of the sample bottles are also so that the rinsing head, if it does touch the top of the sample, it would be okay due to the fact it will not leach. The stainless steel is perfectly fine to use and well within the method. So let's take a look at the method summary here on 537. So typically on a 537, you have about 250 mils of sample. You cannot transfer the sample to another bottle, as some of the PFCs may absorb into the surfaces. Make sure all your standards and surrogates are in the sample and homogenize the sample. Conditioning for the cartridge, which is 6 ml with the appropriate volumes of methanol and reagent water. Key point, do not let your cartridge go dry. And load the sample into the conditioned cartridge at the appropriate mils per minute. Once it's complete loading, you would like to air dry the cartridge, rinse the sample bottle with methanol, and wash all the sample flow paths and lines that sample has gone through, as well with that rinsing of the methanol. Collect the extracts and concentrate to dryness under a gentle stream of nitrogen to remove the water-methanol mixture. Once the extracts are evaporated to dryness, add internal standard and the appropriate amount of methanol water solution to bring to a final volume of 1 ml. Always refer to the method of proper extract storage and analyze LCMS. Now, method 537 with automated SPE. Comparison between SDBB and wax media. We're going to condition the cartridge with a various 20 mils of methanol. We have 10 mils per minute and drying for 15 seconds for conditioning that cartridge. Next, again, another 10 mils. No drying, just soaking for 60 seconds. Reagent water will be the next conditioning step at 10 mils per minute. Then we'll be loading the sample. It will be delivered to the cartridge at 50 mils per minute. Will load at 50 mils per minute, but delivered through the cartridge at a very slow 4 mils per minute with an automated system. We're rinsing the sample bottle with reagent water. We're going to repeat that 7 times with 2.5 mils. Load all the sample at 15 mils per minute, which is going to be that rinsing of the reagent water. Again, delivering at very slow rates. Once that's all delivered through the cartridge, dry for 5 minutes. And again, rinsing the sample bottle with the extraction solvent, 3 mils of methanol, and repeat that 3 times. We're going to clean up the rinse, bring it through, and elute that at 4 mils per minute through the system and drying for 60 seconds. As for the SDB cartridge, for the wax cartridge, same procedure, except we're going to be starting off with 5 mils of 2% solution, ammonium hydroxide with methanol at 10 mils per minute, and we're going to be rinsing again with different solvents of the same 2% moving forward. All right. Now, automated platform cleaning functions. When selecting an automated system, make sure the system has functions to clean itself automatically. Functions such as cleaning system tubing. That's the tubing throughout the entire system, not just the valves, but the tubing in between the plungers, the lines, the reagent valves, the sample valves, and the plunger. These types of functions should be able to be implemented at the beginning and or at the end of a run to ensure it is clean and that no cross-contamination will occur with the following sample. So how do you avoid cross-contamination or leaching of PTFEs? Here's a general method I would use to clean sample lines within the system that would ensure that my sample and transfer lines are contaminant-free. Observe here the 5-second dry times. We spoke about that earlier. You don't want to have any methanol in those lines soaking, even if it's in between samples. It's nice to have it implemented in there, but especially at the end of the day, you want to make sure those are dry. So having this in your method, or at least at the end of your run, at the end of the day, on any automated system, make sure there is a purge of the lines, especially your solvent transfer lines and sample transfer lines. So here we have demonstrating extraction platform background. This particular case here is with no SPE cartridge. So what we're doing here is demonstrating all the components within an automated system with FEP tubing, and it has no SPE cartridge. Each run, we have a total of we have 6 runs here, has 2 sets of lines due to the rinsing function. So if we take a look at the first set, we have sample lines 1 and 7, 2 and 8, 3 and 9, all the way up to 6 and 12. We have the internal standards we used. We have a concentration of 50, 100, and 200. The spiking circuits were not used, but were quantified for background purposes. If we take a look at the first sample, lines 1 and 7, it has the highest of all the positions, but has very low background. I've highlighted a few from this list that are consistent at 0.1 or higher across the board. These numbers are well below any typical requirement for 1/3 the method reporting limit. So here we're looking at the background with an SPE cartridge. We have all reagents, solvent lines, valves, plungers, and cartridges were tested with this system. There are some elevated numbers for PFHA in sample lines 1 through 7, which is sample 1, and in sample 4. The same is true for PFOA. And positions 1 and 4 show elevated levels, which are still low but demonstrate that a cartridge may have made an impact on those positions 1 and 4. Some trouble compounds that are in 537 that are not in the method, but in the 537 modified, they're there. I want to point out a couple here. PFOS has definitely a recovery issue when it comes to concentration. You can have a great recovery, but the blowdown needs to be gentle, not vigorous, but still with care, you will experience a lower recovery. With the SPE part, PFBA, this compound, along with PFPA, does not retain well with SDVB media and will be recovered much better with the wax media. Here we're looking at the use of disposable filters, which are in line with sample transfer lines. If you're running a 537 modified method, have about 24 compounds here, which we're displaying, most likely it will not be a perfect drinking water type matrix. Be along the lines of wastewater, groundwater, may have particulates. Either way, it's something that will have a matrix in the sample in which you would not like to have in your system. It may cause possible problems. So inline filters are an option. You want to make sure that you have the correct inline filter. If you don't, you could be causing, again, contamination within the system. Here we're demonstrating a 3-micron polypropylene filter, which is in line with the sample transfer lines. surrogates are spiked at 20 and internal standards were added but not displayed due to space. The low background is demonstrated with this filter as the method was performed with an LRB. Here are the spike recovery and carryover measurements. Here we have surrogates for both the samples and the LRB are both at 20 and recovering very well. With this 537 modified spike, we can see that the PFOS recovers low, as expected, we spoke about earlier, due to its volatility properties. And we have the PFBA extracted very well. This was done with a wax cartridge. The LRB was run after and had very low background for this first half of the compound list. This is the same sample, but second half of the compounds. Not highlighted, but the fifth compound from the bottom, PFPA, recovered at 97.65. This was one of the compounds we spoke about earlier that does not recover well with SDPB, but does with wax. Besides PFOS at 28%, PFTDA was the lowest at 74%. The LRB was all non-detect for the second half of the compound list. Spike recovery and carryover measurement. This is actually a laboratory 4-5 blank spike at 250. The surrogates were spiked at 20. This sample was diluted at 10 times. Take notice by the actual measurements at 28.70. The LRB shows some background, with only PFBS was spiked on this half of the list at this elevated level. It did not spike all the compounds, only abbreviated list. The spike recovery and carryover measurements of the second half, we have 26, 28, 24, 26. We're right in line. We're hitting that recovery range right around 100. We have minimal background here with one compound at 0.23. Now we're looking at a more elevated spike, and this is at 2,500. Again, spikes, surrogates were spiked at 20, but at this level, they are not available due to the dilution. We have no carryover with PFBS in our LLB after, and we do have some background with PFDA. This is the second half of the abbreviated list. Same sample, great recoveries, all in that 100 range. Again, we diluted 100 times on this sample. But we do have some background here from these samples. Now, in conclusion, you want to make sure all components are tested for known analytes. I think we demonstrate how to do that today on a number of platforms. And you have to remember, it's not possible to remove all PFA background contamination, but the measures demonstrated here today will help minimize that background levels and also cross-contamination. To ensure all components on your platform, the sample flow path can be rinsed with methanol, either manual or automated. Key point, clear out solvent transfer lines. It's one of those pieces where you don't really think about, but if you do have PTFE, that will leach in there unless your system is purged multiple times before starting the next day or the next sample set. Within that day, there is a potential for contamination. Something very simple with PTFE lines, take them out of the solvent delivery bottles right after you use it. You're going home or at the end of the day. I'd like to thank you all for attending. That's the end of the presentation. Now we will take questions.
Well, thank you very much for offering those insights. Before we get started on the question and answer session, I would like to remind our audience how to submit questions. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of the presentation window, and we'll try to answer as many questions as we can. And the first question is, I extract both drinking water and wastewater samples. can I process both on the same system, or do I need separate systems for each matrix type?
Great question. Yes, you can process both drinking water and wastewater on both systems. That just depends on making sure that your sample lines are cleaned to ensure that there's no cross-contamination, whether it be, like I said, on manual or automated. The solvent lines for the solvent lines on the systems also need to be blown out to ensure that there's no cross-contamination of from batch to batch, from overnight, or PF for any Teflon that may be in that line to carry over the next day. So cleaning is absolutely the number one criteria for that question.
Okay, thank you very much. And why is the 24 compound PFC list more challenging than the 14 compound PFC list?
Great question. It's more challenging because there's more compounds and they require a different type of media. For instance, we have PFBA, PFPA. They don't retain well on the 14 compound list with the SDV media. They need the wax media in order to retain and come off. That's the additional rinsing we went over on one of the slides there for elutions. Some other compounds on the list there, for instance, PFOSA, which is on the 24 compound list, is very volatile. That needs a gentle stream of nitrogen. So within the list, the 14 compound list, very basic, will retain very well per that method. But the changes with the 537 modified with the 24 compound list, if you are going into that, you will need to move towards a wax media and be very gentle with concentrating and blowing down with your nitrogen system.
Okay, thank you. And would there be any reason to use a SDVB cartridge over a wax cartridge?
Yes, we mentioned a little bit about that. That is due to the fact that the modified 537 method, if you are looking at all those compounds, you will need to use that wax method. The 537 drinking water per EPA requires the SDVB media for those 14 only, and does not require the wax media cartridge.
Okay, thank you. And someone else wants to know, I'm doing PFC extractions and I'm struggling with contamination issues. What are the sources that are most likely causing this contamination?
Well, that depends on the extraction platform. Manual, it's automated, also depends on the back end concentration, drying, etc. So what I would do is if you went through a number of steps in which we spoke about, one that you can do is work backwards, meaning do a concentration, perform a concentration with the methanol solution and surrogates. There on the back end, you'll identify the components on the back end when you analyze, and you'll already know from what's going on from the extraction and the concentration. So by elimination, process of elimination, you'll be able to segregate the two and have an understanding of if there's any contamination that you're experiencing in the extraction step and you ran it in the concentration step separately and it comes out cleaner in the concentration step, you know that's coming from your extraction step, and you'll need to go through those pieces a little bit more defined of where this could be possibly coming from. Lines, methanol, reagent valves, fittings. It could be the solvent stone. A number of pieces, but by putting the emphasis on breaking it down and concentrating and analyzing in certain parts of the process, because it might not just be the extraction, that's going to help you identify and come to a possible conclusion.
Okay, thank you very much. And what do you consider a long idle time for rinsing a system?
Could you repeat that, please?
What do you consider a long idle time for rinsing a system?
Oh, what do you consider a long idle time for rinsing a system? If you have a manual system, that can be done in real time. It should not take too long based on placing and pulling the methanol through. Should be a matter of minutes. And there's not a lot of components within a manual system, whether it's the large volume or it's just a small inline. The automated versions should have the steps involved, and that just depends on the vendor's process. Each one, I'm assuming, is different, but they absolutely should have cleaning functions within there, and they should be in a timely manner for minutes for the steps.
Okay, thanks again. And the next question is, when you remove the solvent line after a run, how would you store the line to prevent further contamination between uses?
Great question. As long as it's not in the solvent, that's your number one concern. If it's PTFE, you do not want to have it stored in there. You don't want to put it in tin foil, obviously. That is an area in which you would have to go in and understand that this would have to be a study there. That's one thing where I would put it in probably a contained empty bottle, sealed. I wouldn't put it outside in the atmosphere, not in tinfoil, not in a bag. Probably have a empty bottle there so that you can place it in there and it's not in contact with any solvent.
Okay, thanks again. And what disposable inline filters were used?
Oh, yes. These were 3-micron polypropylene, I believe.
Okay, thank you.
If this is a part number you'd like, you can reach back out. We can make sure you have that.
And someone else wants to know, is there any contamination in the LC-MS part of the method?
Yes, there could be. There could be. The same applies for lines, solvent lines that go into the system. So again, you don't want to leave your solvent lines into the methanol for a long period of time between idle times. That can lead to contamination. That's why you should look into peak for that. That is one of the main parts for the LCMS.
Okay, and thank you. The next question is, how do you address a dirty matrix such as leachate from firefighting foam, for example?
Excellent. Great question. The dirty matrix is part of that firefighting foam. Firefighting foam, if the filter, if you have a large concentration of that, if you are going to an automated system, we implement that filter. That helps. That filter will also be rinsed with your solvents, so any residuals, if there is any in there, will be rinsed thoroughly.
Okay, thank you again. And did you repeat this experiment over multiple days for the automated extraction system? If so, how well did the results agree?
Great question. Yes, we did run this on multiple systems and multiple days, and it resulted very well. Extremely low background. Results were very consistent. Cross-contamination was nil to none, but that's due to the automated features of cleaning. So we wanted to make sure that we had idle times in there. We wanted to make sure that we had the samples for the cross-contamination in there. We addressed all of those concerns with the studies that were displayed. Great question.
Okay, thank you again. So thank you very much for answering those questions and for both of you for a great presentation. Unfortunately, we're out of time. I want to thank the audience for attending and for participating in today's event. I would also like to thank our sponsor, Biotage, for making today's educational webcast possible. You will receive an email from LCGC alerting you when this webcast will be available for replay. We do invite you to send this announcement to any of your colleagues who may have missed today's live event. And thank you very much for attending, and we look forward to seeing you here again. Goodbye.